Good morning, guys. I hope everybody's doing well today. I know you guys didn't have class yesterday. You had a session with the apologetics team from Bob Jones University. I hope that was a success. I really think it's important for you guys to be challenged so that you know what to do when you are challenged with your faith. And I hope that was helpful for you. Plus, you got out of class, so that was at least some good could come from it, right? So that's good. I hope everything went well with that. I want to talk to you guys a little bit about the lesson today. It's an interesting lesson. It talks about the title, obviously, 8.2, inverse relations and functions. It's a pretty intriguing lesson. What we have to do here is we got to really think through what an inverse is. An inverse, if I ask you a question, for instance, what's the inverse of 2, you would flip it and you would say, well, it's got to be 1/2. If I asked you what the inverse of 3 over 2 is, you would say, oh, I got to flip that. That's 3 over 2. The inverse of that would be 2 over 3. So we're going to be talking kind of about that, but it's about functions, so it's a little bit different. There's a couple of rules you have to get down, and if you'll take good notes in this lesson, it's actually pretty simple, and I think you'll find this pretty intriguing. Now, we're going to talk a little bit about some things about why and what's going on here when it comes to functions. There's something that you need to get down here. The question here, what visual test can be used to verify that the curves that were supposed to be graphed on the previous one, I'm just not going to graph those. What determines if something is a function or not? There's a very simple, quick test for me to use and to determine if something is a function, and that's the vertical line test. So if I graph anything, I could graph a line, just a straight line. There it is. And I could say, is this a function? And literally, all you have to do is draw a vertical line. And if you draw a vertical line straight through that function or that curve or the line, the drawing, and it intersects in one spot everywhere, then sure enough, it's going to be a function. It passes the vertical line test. Well, what happens, Mr. Collin, if it's like a parabola? You know, we've graphed parabolas this year, and it goes up like this, and it's going to go over like this. Is that a function? Well, you do the same thing. You just draw vertical lines, and if all of the vertical lines intersect in one spot, each line intersects in one spot, then you know it's a function. You know, some of you may say, well, Mr. Collin, can you give us an example that would not be a function? Sure, absolutely. Let's take that parabola we just drew and let's draw it on its side. All right, so you draw that parabola on its side and you draw a vertical line. If I draw a vertical line here, you'll notice that vertical line intersects this graph in two places. So since it intersects in two places, we know this is not a function. So that's a quick visual way to tell if something is a function or not. Pretty quick, pretty simple. If a relationship R, just any kind of set points R, contains an ordered pair A and B. So we're just saying you got an ordered pair, guys. No big deal. 2 and 3, 4 and 7, an ordered pair. Its inverse relation, R sub R to the negative 1, this is always the sign for an inverse. Anything to the negative first power is the inverse. It contains the ordered pair B and A. So if I give you coordinates A and B, and they're in set R, and then I say, what would the coordinates be of the inverse? Well, literally, guys, the inverse, you just switch the points around. Super simple. So if the coordinates were 3 and 2, and I said, okay, that's the R set, what would the inverse of R be? Simple. You literally just switch the two. It's that easy. So you would actually could plot them out and determine what the inverse function would be. Or the drawing, if it's a graph, if it's a line, a parabola, whatever it may be, you can actually figure that out pretty quickly by doing that. The domain and the range of a relation are also switched to obtain the inverse domain and range. So if the domain is x is greater than 3, you would switch that, and when you would say the range would be greater than 3. So that's how it works. Here's an idea. This is what it's talking about. You guys see how you have a set of coordinates here for R, and then we could write them. What they do here is they write them in their function machines. And we've already talked about this, not super difficult. You have 3, so you put 3. You have 8 here and here, so you put it one time. You have A, so you put it there. That's your domain. Your domain, if you guys remember, domain always goes with X. Domain is always with X. So you put the x's there and you draw all their arrows to the corresponding range. Range is always associated with the y. So look what happens, guys. Here r, the first coordinate was 3 and 1. R prime, that's often what it's called if you see something raised to the negative first. R prime, or the inverse of r. You literally just switch the two numbers. Notice, here it's 3 and 1, here it's 1 and 3. And your domain also switches because now, again, the domain applies to the x's. So the x here is 1, and the y here is 3. So that's why they substitute them in there. So you literally see what happens. These pictures just switched, and the x and y coordinates switched, and the domain and range switched. So a function and its inverse, the coefficients in the coordinates just switch around, and the domain and range completely switches. That's the concept that it's trying to get you guys to understand. All right, so literally, we'll skip that. That's an example. We don't need to look at that one right now because I think you guys understand. You literally just switch the coordinates around. All right, when a relation or function is expressed as an equation in x and y, a rule for its inverse can be found by switching the variable in the rule and then solving for y. Let me explain this. This is something you guys will have to learn how to do. It's not hard. There's just 3 steps you have to follow, and it's super easy. I think you guys will find this very easy. I think you hopefully understand the inverse concept. You literally just switch the coordinates around, and that's kind of how it works. But with this, it's a little bit different. So I'm going to work this one step by step. Find the inverse. So we're literally looking for the inverse function of the function that's given to us. So the very first step is to get rid of the f of x and rewrite it as y. So I'm literally taking this and writing it as y equals 2x plus 4. So your first step in finding the inverse of a function is to replace f of x with y. Step number 1, make sure you get it down. Again, substitute y in for f of x. Get rid of the f of x. The next thing that you do to find f to the negative first, or the inverse of your f of x function, is to switch the x and y. You literally replace y with x and x with y. Okay? Again, so the first step is write it as y equals, get rid of the f of x. The second step is to literally switch the x and y letters. So by doing that, and then after you do that, you want to solve the equation for y. So those are the 3 steps. I'm going to give them to you again. Step number 1, get rid of f of x and put y in the place of it. Step number 2, switch the x and y variables. You literally just switch the letters. Step number 3, solve that equation for y. So you can see what they do here. They move the 4 over to this side, and it becomes negative 4. And then you just divide everything by 2. You can split it apart as fractions. It does skip a step there. If you split it apart, it's x over 2 minus 4 over 2, which does reduce down to 1/2 x minus 2. That's the answer that you get. So 1/2 x minus 2 and 2x plus 4 are inverses of each other. Now, what's interesting about this, if just like on an inverse, if I give you a fraction 3 over 1, if I multiply that times its inverse, it will give me 1. Well, the same thing is true with these. If you multiply a function times its inverse, it should always give you 1. So that's the purpose of finding the inverse of a function. Here's another example, just to make sure we know what to do here. Find the inverse, okay? So get rid of the g of x. That's the very first step, and replace it with y. So y equals x squared minus 2. The next step, again, is to literally switch the x and y letters. And then it's as simple as solving for y. They move that negative 2 over, and then you have y squared here, guys. So you guys remember, you have to take the square root of both sides. Always remember, though, if you take the square root of both sides, it's always plus or minus. Don't forget that. It has to be included in your answer. So that's how you find the inverse of a function. Again, not too bad. Pretty simple. Again, the rules that you have to have written down for finding the inverse of a function is to get rid of the f of x, or g of x in this case, by replacing it with y. Then you literally switch the x and y letters, the variables, and then you solve the new equation for y. These are just some examples, the pictures here, of showing you what the functions look like. In this particular graph, this is the f of x function, and this is actually what the f of the f of negative 1 of x is equal to. And they switch the coordinates up. And I'll give you an example. If I ask you guys what's this coordinate right here, hopefully y'all could tell me the x coordinate there is 2 and the y coordinate is 0. So let's switch those around. Let's go to the coordinate 0 and 2. Well, x is 0 and y is 2. It's going to flip those around, and it's going to give us, well, it looks like it gives us this number right here, which is going to be, oh, that's why, because this should be negative 2. I'm sorry. Negative 2 and 0. You flip them around, and this is going to give you 0 and negative 2. That's how it works. If you plotted all the points out, you can actually graph them. Now, the one on the right side is a little bit more complicated. This is the f of x function, but notice the inverse of that parabola, f of negative 1 of x, actually shifts around. And instead of being of this being the vertex is shifted over here, which is interesting because if you look at the picture on the left, if you draw a vertical line straight down, it intersects one spot there, so that one's a function. It intersects one spot there, so that line's a function. But look what happens if you do this. If I draw a vertical line through this one, the blue graph actually is a function, but the red graph is not a function because it intersects two places. So it is possible that the inverse of a given function may not be a function, which is kind of odd, but that's actually what takes place. Okay, the horizontal line test. We've talked about the vertical line test. The horizontal line test says that if a horizontal line can be drawn through more than one point of a function's graph, then its inverse is not a function. So go back to that previous picture that I had, where I had the parabola here, and then we had the inverse already drawn. Notice the horizontal line test, when I draw it through there, it intersects in two spots. So the horizontal line test told us, again, if I were to graph the inverse, it would look like this. We know that doesn't pass the vertical line test. Well, we could have known that at the very beginning because of the horizontal line test. If a graph does not pass the horizontal line test, then you immediately know that its inverse is not a function. And that's what this is illustrating. Any function whose inverse is also a function is said to be a one-to-one function. This means it actually passes the vertical and the horizontal line test. If you have a line that or a graph that passes both, then it's said to be a one-to-one function. Literally, it's a one-to-one, meaning one coordinate is exactly corresponds to another coordinate. It's a one-to-one function. So it passes the vertical and the horizontal line test. It is considered a one-to-one function. Okay, so the question is, now that we have an understanding or somewhat of an understanding of a function and its inverse, how can I tell if two functions are inverses of each other? Well, that's where you see this relationship. If you can say f of negative 1 of f of x is and f of negative 1 of x, if they are equal to x, then the functions are inverses of one another. So if y'all remember what we did on Monday where we had f of g of x, if y'all remember this, hopefully you do. This meant you literally took the g function and you plugged it into the f function. That's what we're doing here. And if you do that and you get both of them equal x, then the functions are inverses of each other. This is the complex. You see this picture on page 339. It's not super complex. It just kind of shows us some things. Here, I take 10 and I plug it into my f of x function. I get 24. And then I plug 24 into this function's inverse. So what we just learned just a moment ago, this is the inverse, and I get 10. So here, same thing. 10, you plug it into the f of negative 1, the inverse function, you get 3. You plug that back into the f of x function, and I get 10. They're both equal to each other, so therefore these are considered inverses of one another. But what you guys are going to have to do is you're going to have to look at two functions and tell me if they're inverses of each other or not. So this isn't super hard, but it is going to take a little bit of practice because this is relatively new, evaluating f of g, composite functions or composition functions. So to evaluate this, guys, I literally want to evaluate h. You can evaluate it either order. They choose to do g of h of x. G of h of x is the same thing as me saying, just to help you guys understand, g of f of x. I'm sorry, not g of f. g of h of x, which literally means you take the h function and substitute it to the g function where there's x. So you guys can kind of see what they do here. They take this function and they're going to plug it into the g function where there's x. So that's what they do. They take the, again, x function and plug it into the g function where there's x. So you do some distributive property here, but actually this one's going to be easy because the 4's cancel. So when the 4's cancel, you get x plus 1 minus 1, which gives us x. That's awesome. That's half of the process because we said that g of h of x is equal to x, and that's what we wanted it to be equal to. Now what you have to do is you have to do the opposite. You have to say you have to say h of g of x. Yes, it looks like hog, but it's h of g of x. So again, hopefully y'all remember, this means you take the g of x value expression and you plug it into the h value where there's x. I take the g of x value and I plug it into the x value right there. So the screen will have the work here for you guys to see. I plug it in, and that's what that gives me. So again, it's simplification here. The 1's will cancel out, which is convenient. So I'm left with 4x over 4, which gives me x. So sure enough, in this particular example, g of f of x equaled x. And we just showed that h of g of x equaled x. Since they both equal x, we know that the functions are inverses of each other. Now guys, listen very carefully. If you go through this process and you don't get x, you get something else. Maybe you do the work and you get 1 and 1. That is not an inverse function. They have to be equal to x, both of them. Let's say you do all the work and you get x and you get x squared. Well, they are not both x. They have to both be x in order to be inverses of each other. So that's the concept there involved. You got to make sure you know how to do that. Very, very important, okay? Inverse relations have a one-to-one relation for every element in the domain. There is a unique element in the range. It's like a one-to-one function, okay? There is a unique element in the domain as well. So here's an example. Given the h of x is equal to square root of x minus 3, find the rule for h of negative 1. So here again, guys, we're looking for the inverse. Hopefully you remember the steps. First step is to replace the h of x or whatever, the f of x or h of x or g of x, whatever it is, this piece right here, you replace it with y. That's the first step. Again, you should have all this written down in your notes. Second step is to literally switch x and y. And then you solve the equation for y. Now here, guys, you got to square both sides. That's where they got this next step. And then you solve and you get y is equal to x squared plus 3. Just another example. State the inverse is domain and range. The inverse you just found. So the domain here of the original function of the h of x function, this cannot be less than 3, because if it is, it would give us a negative number underneath the radical. That's why you say the domain for the h function is x is greater than or equal to 3. Now if you look at the inverse, the r is the inverse, that's what they, or the range, I'm sorry, the range will be greater than 0, because the value for the y will not be anything less than 0. Here you guys see, if we apply that, the domain cannot be, it has to be greater than 0. And then when we solve for the range of the inverse, we find that the range is y is greater than or equal to 3. Because again, this piece right here cannot be less than 3. It asks you to graph it. I'm not going to have you graph this, but if you did, this is what it would look like. You can see the starting points there, and you can see the original function here, and then the inverse function here. Okay, guys, so that's the lesson. I know it's quite challenging. There's a lot of material that's been covered, but I think you guys will do okay on this. It's just going to take a little bit of practice. So your homework will actually come in very handy here. So go ahead and pay attention to the screen. I'm going to go ahead and put your homework on the screen here for you guys. You guys will need to complete, off of this lesson 8.2, 1, 4, 5, 7, 9, 11, 14, 17, 21 through 23. Well, yeah, we'll do it this way. 21, 23, 24, and 29, 30, 35, and then let's actually make that 33 through 35, 48 through 49, and then 54. It seems like a lot of work, but I promise it's not that difficult, okay? You're going to run into some that's a little bit more challenging, but we're going to take a look at some of these. I want us to practice a couple of these. So go ahead and flip over to the lesson. The homework starts on page 341. So on this page, we'll see a couple of things here. The first section here says simply represent its inverse as a set of ordered pairs, and then determine whether the inverse is a function or not. So number one, again, it's really not too difficult to figure out an inverse. Number one actually gives us the coordinates. So the coordinates that it gives us are 1 and 5, 6 and 2, and 7 and -4. Well, remember what I said about a function? In this case, it gives us the coordinates and its inverse. You literally, guys, it's super simple. Y'all probably would love a test of this. You literally just switch the coordinates around. So this is 5 and 1. The next one will be 2 and 6. The next one will be -4 and 7. It is that simple. That is your answer for the first section for number one. That's representing. Then determine if it's an inverse or not. This is going to be an inverse because it is. It literally, you just switch the coordinates around. So the answer to the second question B is this an inverse? And your answer is yes, this is an inverse because all of the x's and y's are perfectly switched around. So that's how that works. Now, I didn't require you to do number two, but look at number two and you'll understand what I mean with the inverse or not an inverse. Number two, the coordinates are 1 and 2, 5 and 2, and -3 and 2. So if I ask you guys to tell me the inverse of that, hopefully y'all can do that. Pretty simple. You switch the coordinates. 2 and 1, 2 and 5, and 2 and -3. Now the question is, this is the inverse of function. Well, hopefully y'all remember back from Algebra 1 that in order for something to be a function, every x can only have one y. Again, every x can only have one y. Look at the example up top here. This x has one y. This x has its own y, and this has its own y. But if you look at this one that I have at the bottom of the screen, notice this x has a y, but look at this. This x, it's the same x, it's 2 and 2. It has a different y. Also, the last one, this 2 has a different y. So because the x has a different y, the same x I should say, this is not a function. The inverse would not be a function, and that's how you tell. Again, every x has to have one y, and if it does, then you're good to go, and that's how that works. I want to do another one at number 11 here to help you guys out. You do have 11. I tell you what, I want you guys to do number 11. We're going to do, I'm going to do number 13. 13, you have g of x equals -x plus 4. The directions say find the inverse. We got to write the inverse rule. So remember your steps. It's simple process, not hard. Just remember your steps. Again, the first step is to get rid of the g of x, the functional notation, and we want to rewrite it as y. So literally say y equals -x plus 4. That's step number one. Step number two is to literally switch the x variable and the y variable. So I'm literally switching these two variables in the second step. So that would be x, not -x. It's just the variable, no sign, no coefficients, nothing. You literally just switch the letters themselves. So that minus is going to stay with that y. And then the third step is to solve your equation for y. So I need to move the positive 4 over here. So that would give me x minus 4 equals negative y. And then, guys, I need to go ahead and divide everything by negative 1 because I want positive y, not negative y. So that would give me negative x plus 4 is equal to y. If you guys feel more comfortable rewriting that with y first, that's perfectly acceptable. You can do this. So this answer is the inverse of the original function. So pretty simple, not hard at all. Now you're going to come across some that get a little tricky with square roots and squaring and stuff like that, but other than that, it's not very difficult. I think you guys can handle that quite well. The last section of homework that you're going to have to do in perspective of inverses is determining if two functions are inverses of each other. So I'm going to show you one of those to make sure you got it. It's number 23 and 24. That's what you guys will be working on for homework tonight in this perspective, okay? So here's how this works. I'm going to do 25. That way you won't be able to see what it is or one of the answers that you guys have to come up with. So number 25 gives us two functions, g of x, and it says it's equal to negative 2x minus 6. And we also have h of x, which is equal to negative 1/2 x minus 3. Now don't freak out about the fraction. It'll be okay. Remember to test to see if they are inverses or not. You literally have to solve two things. I have to solve for g of f of x, and I have to solve f of g of x. You solve for both of them. And if both of them equal x, then they are inverses. If both of them equal anything but x, they are not inverses. So let's review. I think some of you probably are still having a little bit of trouble of this. Well, I already messed up here. This shouldn't say f. This should say h. Got to stay consistent here. Sorry about that confusion. So the first one says h of g. So I'm literally taking the h function and plugging its value into the g function where there is x. So this right here is the value of h of x. So g of h of x means I take that value and I plug it into where x is. Again, I take this value and substitute it in the place of x. So when I do that, that's going to give me negative 2. Instead of saying x, I'm going to say h of x, which is negative 1/2 x minus 3. And then it's going to be minus 6 because I plugged it in here and I have a minus 6 right there. So guys, all you got to do here is simplify this. Just FOIL this out and everything will be okay. I'm going to end up with, that's going to give me 2x minus, or plus 6, because negative 3 times negative 3 is plus 6. Negative 2 times negative 3 is plus 6. And then I have minus 6. Again, I made a mistake here. Negative 2 times 1/2, negative 1/2 is just x. So let's try that again since I messed it up. Use distributive property. Negative 2 times negative 1/2 is positive 1, so x. Negative 2 times negative 3 is positive 6. And then I have the minus 6 there. So here, guys, you get x plus 6 minus 6, which is equal to x. That's great. That's what it needed to equal. Now I need to do the other piece. I need to solve for g of h. This again means I take the g function and plug it into the h function where there's x. So here's the g function. I'm taking that and I'm substituting it in for x. So I say negative 1/2. I don't say x. I say what it is equal to, the g of x function. Negative 2x minus 6. And then I have a minus 3. Once again, use distributive property, guys. Negative 1/2 times negative 2 is positive x. Negative 1/2 times negative 6 is positive 3. And then I have minus 3. And sure enough, 3 minus 3 is 0, so I get x. So since both of these are x, I know that the two functions are inverses of each other. If you substitute stuff in and you do not get x, you get anything but x, then you know that they are not inverse functions of each other. I hope this is helpful, me actually working some of these homework problems. Just practice some of these. It's not super difficult. You're just going to have to try to think through it. And of course, again, you can watch the video again on your own time to help you with some of the homework. I hope it's been helpful, guys. Looking forward to seeing you guys on Monday, and hope everything works well. Tomorrow, you guys are going to actually be working on some worksheets that will help you with some of this information. So I think that'll help you as well. So you'll be doing that on Friday. But I look forward to seeing everyone on Monday, and I hope you guys have a great rest of the week and a wonderful weekend.